changed his talk, new gauge symmetry in gravity.
You see, it's inspired by this great talk of Dr. Katanayev. I thought I'd tell you first some fundamental things about multivalued fields, because everything has shown us was a special family of solutions which were based on multivalued solutions of the metric. And I want to show you now that there's a very general gauge structure inherent in geometric structures that, that allow you to convert theories with curvature into theories with torsion and backwards. And this idea for that came to me when I saw that Einstein invented roughly in the 1935 the so-called parallel theory of gravity, in which you have only torsion. And everybody knows nowadays in gravity that this theory is completely equivalent to the normal Einstein theory, which has only curvature. And then I remembered that in crystals, the defect structures simulate Einstein-Cartan geometry. Dislocations are translational defects, and they represent torsion. And disclinations are rotational defects, and they represent curvature. And in a crystal, if you take a dislocation, you can recreate the same dislocation by taking a disclination and an anti-disclination at a small distance. And the vice versa, if you have a sequence of disclinations, you can create a dislocation. So if in a crystal the two defects are not really independent, that means that also in a theory of gravity with torsion, you can convert curvature into torsion without changing the physics. And I want to now convince you that, show you how this works, okay? So you see, So you see, this is normal field theory, which you don't believe in. Eh? That's where you have boring fields. Everything smooth, desert, it's boring. But if you have multivalued fields, you have such beautiful landscapes. Eh? So much more interesting. And therefore, I want to propose anybody who has not learned field theory yet, he should start learning immediately multivalued field theory instead of single-valued. And you see, when you have multivalued, you have overhangs, which makes life much more interesting. Eh? Yeah? And you know, if I had the right version of this, I would click it and you would hear that the Bavarians always make when they play around in the mountains, they yodel. You know what yodeling works. I can't do it very well. I can only sing Italian operas, but not yodel. So anyhow, this guy is yodeling now. You have to measure it. So I want to first give you a simple example. You take a complex field theory, like Ginzburg-Landau, with a gradient term. With a gradient term, and you can always split the field into size of a field times the phase, e to the I psi x, yeah? And the normal chain rule that people apply is if you take the gradient of this field, you get the size times gradient of psi plus gradient of rho times e to the I theta. That's the chain rule, Leibniz. So everybody's using it, yeah? And if you insert this here, then the Hamiltonian that you have is this Hamiltonian. And this Hamiltonian has a real field with a gradient, and then the theta field with its own gradient, and then you think you have transformed this Hamiltonian into this Hamiltonian. Yeah? That everybody will believe that. But if you would take the partition function, you would integrate over the rows, the theta fields, and you would get the whole statistical mechanics of the theory. That's what everybody believes. However, this is wrong. Because this theory is in the universality class of the Ising model. So it has critical exponents of the Ising model. And this one is known to have the critical exponent of the XY model, of helium, superfluid helium. The critical exponents of superfluid helium are completely different from those of the Ising model. So you have done something wrong here. But you know, you did something very simple. And how can something be wrong in this? You ask yourself. And the answer is the theta field. The theta field is multivalued. If theta and theta plus 2 pi and 4 pi, they're all the same. So you cannot use Leibniz rule if theta field is multivalued. That's a basic mistake you have done. And that's the reason why you have to improve your theory. That's the most fundamental error in field theory if you have multivalued fields. So to show you what happens, you see if theta jumps by 2 pi, then e to the I theta is invariant. So there is no jumps in e to I theta. And that means if you use the rho and the theta representation, you have to take care of these jumps by 2 pi and multiples of it.
They
Yeah?
are
And
organized
the chain rule has to be corrected. So from the theta field, you have to, from the gradient of the theta.
we have to see what
Calmo,
people,
per
but I
favore.
think there is lots of people we are going
C'è una
to
lezione qua. One center. You see, you have to subtract from theta a delta function on the surfaces over which the jumps take place. The field, the complex field psi, grazie, complex field psi has all these jumps, but the correct gradient is only obtained if you subtract the delta functions on the surfaces. And so the nice property of such delta function on surfaces, how is it defined? It's integral over the surface of the three-dimensional delta function. That is a delta function on the surface. And the nice thing about it is, yeah, you see, if you have the delta function and you're in one dimensions, then you can remove all these jumps by just going to the covering group, U1. And then, so to say, it's all trivial. The difference between multivalued and single valued is trivial. But in more dimensions, and this is where the interesting field theories take place, like 3 dimensions, you have to keep these delta functions. And if you keep these, you see, this is the multivaluedness, this is a staircase here, and the jumps, this is U1, the covering group, and you can just go to the extended, my battery doesn't seem to be good. You go to the extended scheme, and then everything is corrected. But in more dimensions, the delta function on surfaces have this most interesting gauge structure. If you take one surface and shift it to another surface S prime, then you run over a volume V, and the change of delta is a gradient of the delta function on the volume over which the surface has swept. And so, you see, it's just like in gauge theory, you change one field to another and you get an extra gradient. And there is invariant field strength. The curl of this delta function is a delta function on the boundary. So you see, if you shift the delta function with fixed boundary, yeah, the invariant thing is a delta function on that boundary. And if you take an axial gauge, you can take delta 3 of the surface delta function equal to 0, for example, and all the different gauges give to the same delta function on the boundary. And that is typical for gauge theories. And here is, so to say, the mother of the most fundamental gauge theory. It's just a delta function on a surface. Yeah? And no, I also want to show the most simple multivalued field theories. It's the Arcus tangent y over x, or x2 over x1, and the gradient is very simple. You can calculate it. And you see the point is that if you take the commutator of the derivatives of this field, then it's not 0. But you use some, yeah? You want to ask a question? Oh, you can calculate, convert it into a contour integral over a circle, and then you find that there's a 2 pi, and that means the commutator of the derivatives of this field is a delta function at a point, at the origin. Yeah? So this is the most elementary fundamental field theory, where you have non-commuting derivatives. And this allows you to find completely new structures. And we can calculate the Green's function for this. Yeah? You see, if you take the phi as a Green's function, then it solves the equation d1, d2 minus d2, d1 is a source, as a delta function source. And you can use any source if you use this delta function as a Green's function. And then you can use any current and find what the f is for that. Yeah, you just a superposition of this arctangent. And therefore, we can note something important. The logarithm of difference of two complex numbers is a mother of 2 important Green's functions. One is the Poisson equation, that you know the real part of it is a delta function at a point which everybody is using, but the imaginary part is just the Green's function for the commutator of two derivatives. So there's a completely new differential geometry that you can make. And the easiest application of this is magnetostatics. The usual magnetostatics, you use a gauge field A, and the magnetic field is the curl of it, and the curl of the B field is a source, yeah, and you can do this gauge transformation that everybody uses to do all the time. And when you do this, you always assume that the gauge transformation has commuting derivatives. Otherwise, it is not invariant. In fact, if you allow for non-commuting derivatives, you change the B field. That means the typical gauge transformation that we all grew up as students with are those where the derivatives commute. In other words, you never have multivalued gauge transformation. And again, in other words, if you use multivalued gauge transformation, you can change the B field. And that means you can start from the free theory without any magnetic field, just a pure gauge field. And if you gauge transform it with a gauge transformation which has non-commuting derivatives, you create a B field. That means you can create a theory with B field from a theory without B field by a generalized gauge transformation whose derivatives do not commute. And if you tell you this, you might think, oh, crazy stuff, but Dirac created the magnetic monopole that way. And you like Dirac so much, so you will accept also Dirac's creation of magnetic monopoles. Because you see what he's doing is, you take a normal gauge field and you write it as a gradient of a scalar field. And if you want a thin flux tube, you take a scalar field whose derivative don't commute as a delta function, and this is the famous Bohm-Aronoff flux field that you create with a gauge transformation of the multivalued type. You make yourself a thin magnetic field line that way. And it's very simple. Everybody has been doing that, but you can conclude many things which may at first surprise you. Yeah, here's now the monopole. You see in the monopole, you have the gradient of B is magnetic density. And therefore, if you insert the B field as a curl of the A field, you find that the derivatives don't commute. That means the moment you introduce a monopole a la Dirac, you're working with gauge fields which do not have commuting derivatives. And that means if you insert here again the gradient of lambda, you find a lambda whose triple derivatives don't commute. That's one step further than we just discussed. And therefore, the moment you work with monopoles, you can play also with derivatives of gauge fields which do not commute. Yeah? And now we can derive the following. We get a very important result. We can derive minimal coupling from assuming that the theory without field is arising from the theory with field is arising from the theory without field by just doing this multivalued gauge transformation. Because take just a free particle, eh? And the free particle is invariant if you change the Lagrangian by such a term, which is a pure gradient term, with a lambda, that is the usual gauge invariance of a free particle. And now the point is, you see, the action changes just by a surface term, which means the physics is invariant under this. Yeah? And if you now take lambda to have non-commuting derivatives, which one may call non-holonomic lambdas, multivalued lambdas, you allow for non-trivial A field, as I explained earlier. And therefore you can go to a theory without A field, to a theory with A field, by just replacing this gradient here and put A there. And this is a well-known minimal coupling prescription. That means the minimal coupling, which usually is a prescription, has been derived by assuming that theory with fields is just a non-holonomic image of theories without field. Okay? Very simple. And Schrödinger theory, same thing. Huh? You take the Schrödinger equation, and the gradient has this typical minimal coupling thing, but if you do it just with a pure gauge transformation, then you can do it without problem. And it's not coupled to electromagnetism yet. But the moment you now assume that this gradient here, you just take the solution that you know and you multiply by this phase, and then it's still a solution of this more complicated problem without any problem. But if you now allow this lambda to be multivalued, I have another pointer. This pointer has given up its spirit. Yeah. Ah, yeah. This is. You see, if you allow this now to be multivalued, then this becomes the A field. Huh? This becomes the A field, and then you have typical minimal coupling. So you see, I have derived the famous rule of minimal coupling as a consequence of a non-holonomic mapping of free theory into interacting theory. Now, your head will ring about immediately when you see that. The same thing you can do with gravity. You can take a theory without gravity, what your famous empty space, where you just have Lorentz invariance, and I introduce gravity this way. I just transform flat space, which is just the same thing as here, pure gauge transformation. Here I have some more insertion. Yeah, I have one more insertion, which I don't know whether I want to show to because it wastes our time. But you know, if you take a current along a loop and you calculate its magnetic field, you can easily replace it by gradient of a scalar field. You don't use your usual Maxwell construction, and the scalar field is just the angle, the spherical angle under which you see the loop. And if you take this, and the gradient of it is exactly the right magnetic field. But this construction has a jumping surface here. It has a jumping surface by 4 pi, and you can shift it anywhere. And this is the gauge transformation I showed you with the delta function on the surface. You take the delta function of a surface, shift it here or here, you always have the same B field. Yeah? And so there is an equivalent construction of magnetic fields in terms of scalar fields if you allow the scalar field to be multivalued. So here is just the equation word, and you can take the action for this. You have to subtract then the delta function on that surface has to be subtracted, and then you just do some identity transformations, yeah, and then you find Maxwell theory from it. It's no problem to go to Maxwell theory, yeah, and here I show you that the B field is divergenceless, and you can write it as curl of A field, and then automatically you get Maxwell theory, yeah. And you have another type of gauge transformation than the Maxwell one, which is completely equivalent. You have a multivalued gauge transformation which completely replaces usual Maxwell gauge transformation. Completely equivalent formulation. And that's why superfluid helium and the forces between vortex lines can be redescribed a la Maxwell as Biot-Savart type of forces. Then you do the opposite, because there you start with a gradient of omega, and by doing this, what I just did for you, you go to the Maxwell description of vortex lines in superfluid helium. Okay? So anyhow, this I explain here in this slide. But now we go to something that, well, maybe I should. Yeah. What I want to show you only, if you have superfluid helium and you take the ensemble of vortex lines in it, then you can describe them obviously by some Maxwell type of theory with lots of lines with forces which are Biot-Savart-like, and then you can make a new theory of superfluid helium which is not based on a complex field but based on the disorder fields of vortex lines. And for this I've written this book on disorder fields here in '89, where you can read this all. It's a beautiful way of rewriting normal superfluid helium theory in terms of a disorder theory where the fundamental particles are not the helium atoms, but they are the vortex lines in superfluid. And this is a very nice description, because when you cool helium down to 0 temperature, it's a vacuum for vortex lines. So you have a nicer description than the Loschmidt-Zahl number of helium atoms, which make a big chaos. Instead of that, you have a vacuum of vortex lines, and when you heat, you get first small vortex lines, which are protons a la Landau, and then if you heat more, they get longer and longer, and then there comes a point where the vortex lines fill the whole volume, and what happens then? The inside of a vortex line is normal fluid, and so the whole liquid becomes normal. And therefore you can redescribe the superfluid helium transition instead of a complex field theory, as everybody does in Bose-Einstein and so on. You can redescribe it as a disorder field theory where the vortex lines proliferate. And the point why field theory is good for that, you know that usually field theory you use to describe the fluctuating paths of particles in quantum theory, but you can also use it to describe the fluctuating vortex lines, just as if they were particles, and it's completely equivalent. And that is the disorder field theory. You know, Landau became important because he invented the order field theory, and I make the counterpart here with the disorder field theory. And that's why I'm infamous, okay? So, and you know, you see that this book has 2 volumes. One is 700 pages on this, and one is 700 pages. And here you have also differential geometry and crystal melting, because that's the second volume, which is also from 89. And there I proposed first the theory which Katanaev showed us here, namely that you can convert curvature into torsion anyway. But since nobody has noticed it, I had to write more papers on it. And I had to write a whole book, which is called Multivalued Fields, because this thing was too old. People forget books that are older than 2 years. And therefore, I had to write a completely new book. Anyhow, so therefore, the theory of superfluid helium, which usually is described by one complex helium field, is here described by one complex field whose Feynman diagrams are pictures of the vortex lines, and a gauge field which describes the forces between vortex lines. And this is so-called dual theory of superfluid helium, from which you describe all properties, all critical exponents of superfluid helium. So, and now comes the story, the culminus, for which you may have been waiting, because if you do non-holonomic coordinate transformations, then you can create a space with curvature and torsion from a flat space. And I'm doing the same thing. And first we make some pictures to illustrate that. And that's these old pictures, which Katanaev was shown already, that if you have a regular crystal and you put a line of missing, a plane of missing atoms in there, then this is called a dislocation. And then there are dislocations of various types. Yeah, this is this edge dislocation, screw dislocation, and there's a Burgers vector, and so on. And then there's also curvature defects in which a whole cut is missing. Yeah? And then you can make simple models for the dislocation, which I write down, but you don't need to watch them properly here. And then when you have understood this, you can derive all geometry of Riemann-Cartan spaces from just the gradients of a dislocation of a displacement field, and studying and allowing for the commutators to be non-zero. And if you keep track of all the commutators, you can rederive all Riemann-Cartan geometry from that. And I won't go into details yet. Yeah? And now I want to show you something which follows also from this assumption that curved space physics is just flat space physics after a non-holonomic coordinate transformation. You take a free particle, and if you just do a normal coordinate transformation, then you get a metric which is called the induced metric. And the space is still flat. It hasn't changed at all. It's just a redescription of flat space physics. Yeah? And you derive the typical Christoffel symbols. Yeah? And I put a bar on top. The bar means it's Riemannian-like, because I will allow for torsion without the bar. And you see, now comes quantum physics. Now, nobody knows really what a particle in quantum physics, what equation it obeys, because the Einstein axiom that if you drop a point particle, it is behaving like a free particle, like it's being in Minkowski space in its surrounding, that it doesn't apply here, because a point particle does not remain a point if it's quantum physics. It's a packet. And if you have a packet, the packet is subject to tidal forces. And nobody knows what it is, but my principle tells you what it is, because you do this transformation, and then the normal gradient square becomes a Laplace Beltrami operator. And then people have been writing lots of papers disputing how much R you can add, because for dimensional reasons, you can allow for any amount of R. And people have done many different considerations. Some people find 1/24. Bryce DeWitt finds 1/12, then other guys find 1/8, and so on. And so there's a big dispute what there is. And since there is no experiment really, the dispute is open. But I tell you now from my principle, which of course can be wrong, but I would suggest that the image of the free space Hamiltonian, of the flat space Hamiltonian, under the non-holonomic image is the correct one. And then it turns out, and this is in my book on path integrals, which somebody might have seen, If you don't, you can download it from the internet. And so you can do just the coordinate transformation, yeah, and allow for the usual coordinate transformation as computing derivatives. But if you allow, and here you define the 4-bind and so on, the usual story, and you see if you now assume that this is not 0, then you have from here, you have torsion, and from here you have curvature. And then it's very easy to define curvature tensor, torsion tensor, and so on. It follows automatically from the non-commuting derivatives. Okay? And I don't do this for you here now, all. But you see, this is, for example, the non-commuting derivatives of this 4-bind field give immediately the curvature tensor. Yeah? And the non-commuting derivative of the, in this form, of the X itself is a torsion tensor. So it's very simple geometric structure which follows automatically. And all the mathematics of Riemann-Cartan space is trivial there. So, and the integrability conditions that follow from what I just told you are just that you want that the G mu nu is observable. So that has commuting derivatives. And the gamma is also observable, has also commuting derivatives. So if you assume those, you get automatically all Bianchi identities that you know of. Yeah, that is the one for the conservation of energy, and the other one which comes from the torsion, yeah, the Bianchi identities. And then this is the famous conservation law that leads to the asymmetry of the energy momentum tensor. Okay, and here the Bianchi identity. Okay, but that structure, okay, you can read up in the literature in my book, yeah. Now, the other story is if you take this whole thing on a lattice, you can just write elasticity as a difference of the plastic gradient and the elastic gradient. And there's, of course, in general also a Poisson term, but for the discussion here in the lecture, it's not worthwhile writing it down. But I just want you to understand the principle of it. If you take this on a lattice, it has this form. Then you have the gradient of the displacement field, and then you have the plastic field is just jump fields. And if you take this model and study it on a computer, you find a melting transition, because at some place, the defects which are contained in here proliferate like in helium, and the space is filled with defects, and then the...
No interruption while during the talk, please. No interruption. Please finish your talk. Sorry.
Oh, battery is gone. Okay. So therefore you see, by introducing defects on a crystal, you get the melting transition, and this is this second volume that I told you about. And now when you have understood this, you see that you can make a theory of gravity by assuming that we are living in a world crystal which is filled with defects. And these defects in principle have two types, dislocation and disclination, and they make the Riemann-Cartan geometry. But what I told you earlier is that they're dependent on each other. That means you can choose whether you fill your space with rotational defects or translational defects. It doesn't matter, it's just another description of it. And Einstein has chosen the way with rotational defects, but you may choose a way with translational defects. But it's the same theory. And Kardashev has shown us that he has found what is called a dislocation infinite line, in which he has also two descriptions of it. It's a particular example of this general theory here. Yeah. Okay. And now, therefore, let me just go ahead. Yeah. And therefore, you see, I write a world crystal model, and I can check in it that I find the forces. But the point is, if you want the real Newton forces, you cannot use this model. If you use this model, then the disclinations have an R type of force and not a 1/R force. Therefore, what you have to do is you have to introduce one gradient here. Yeah, you have to introduce. Where is it? You have to put another gradient in here, and that kind of gradient is generated if you have dislocations proliferating. Like in helium, the vortex lines proliferate. If you have dislocation lines proliferate, then you get an additional gradient here, and then it's called a liquid crystal. That's a typical theory of liquid. So for a liquid crystal, then the forces are Newton-like. And well, this is just detailed equations. I don't want to bother you with them. But you can prove everything what I said with equations, okay? It's not just words. It's also Greek letters. Huh? And you see, when you do it with the other one, you get 4 derivatives here. And that's the wrong force. It's 1 over k to the 4. That's why you have to first let the dislocations proliferate. Yeah, dislocation proliferate, and then everything comes out right, okay? You see, and this is the wrong force. Huh? And to get right force, you want 1 over d square here. Yeah? And this is you do by one more gradient. And that's what I call a floppy crystal, a floppy world crystal, or call it a world liquid crystal. And that's completely, geometrically, completely equivalent to Einstein theory with the way I did it here, just with curvature. But there's another way of rewriting it completely with torsion. And there's infinitely many ways in between. You can rewrite from curvature to torsion theory, you have infinitely many possibilities of writing it by just doing a multivalued gauge transformation from one to the other. Yeah, and you see, you can, interesting is also if you have a lot of curvature, then like in helium, you may have a molten world crystal. And it would be very interesting that the inside of a black hole is really a molten world crystal. And there could be completely different physics from the Einstein physics from outside when the curvature is weak. Because Einstein physics, proportional to r, the action, is certainly just a linear approximation. And you know that since the times of Sakharov, we have learned that all fluctuating fields in the world create curvature stiffness of the geometry. And the beginning, the smallest term is r, which is Einstein. But if you curve more and more, then r won't be correct anymore. And you will get new terms. And I can show you also a theory which does it, where you can derive that. But if you have high curvature, Einstein is certainly no longer correct. And it will always have correction terms when you get of the order of the Planck length. Huh? Anyhow. So then the question is, what are the world lines of the defects? What objects are they? You see, and they can really be strings that we have been using in string theory, even though string theory so far is the worst theory, the wrongest theory that physics has ever invented, because everything that is predicted by string theory is wrong. But if you think that the strings are just pictures of the defect lines, then everything can become consistent. So because all the particles that are predicted by string theory do not exist, but they could exist as dark matter. And even though Rogero doesn't believe in dark matter, but they could be described by strings. So there is a chance that the string theories have not done only in completely unutilizable work, but maybe they have done some nice pre-work for future discoveries. Huh? And here's the story that I told you earlier, that you see if you have a disclination and you take one anti-disclination, that's the same thing as a dislocation here. Or the opposite, if you have a lot of dislocations, you have one disclination. That's what I told you earlier. The mathematics for this is very easy. I just a picture of it. Okay? And wait. Okay, here's just formalism, which I don't want to bother you with, because I've just too little time for that. Let me see. Yeah, okay, let me just run it through. Another story I should tell you, the people who are thinking torsion is a fundamental field, like Hale or so in Cologne, they are always saying that torsion does not couple to photons, because otherwise photons would be massive. That was already found by Schrödinger in the 30s when he was in where was he? In Dublin, exactly. You know, we went to Dublin because he had 2 wives, but they didn't like it either. Anyhow, and therefore these people don't put torsion into photon theory. But if you put torsion into electron theory, that's what these people all do, then you generate also a mass term. And these people who put torsion into fermion theory, they always ignore that by Feynman diagrams, you also generate mass for the photon. And that they wouldn't like to accept. Then they always say, oh no, the photon remains massless because of gauge invariance. But the gauge invariance does not protect you from masses that are generated by such a Feynman diagram. And that was first shown by Schwinger.
Agent, 5 minutes because we are very late.
Very good. I'm hurry. Sorry, I can stop immediately. Wait. Wait. Oh yeah, wait. Okay, no, I won't tell you this. Wait. Yeah, I just want to show you that this you can read all up in the book, Multivariate Fields, which Cardano has also known, but it didn't appear in his lecture, okay? But this is where the theory is derived, and the book is only 25 euro, and you can download it for free. I give it to you as a present, okay? And okay, sorry. Thank you very much.
Question, please.
Thank you very much for your very nice presentation. I'm going to ask two very short questions. First of all, you're talking about torsion makes the photons massive unless Q is equaling to 1. So I'm going to ask you set Q not equaling to 1. You talk about massive in the sense of, are you talking about a mass of up to something like 10 to the minus 40 G or what? Or
No, the torsion is superfluous in the whole description. You just work with curvature. The torsion does not couple to neither to the photon nor to the electron, because it's just a special description, a funny description of curvature. Therefore, you should not use it, because you can rotate it by gauge transformation completely into curvature.
Another question, please. We are late. Sorry. Quick question, please.
How do you define partial derivative of a multivalued function? Because it has...
Take one value here and then here difference and divide by the distance.
But which branch of a function you must choose?
You take the arcus tangent and play it. I wrote everything down. You put the cut there. You first make a full cut and then you continue analytically through the cut. The usual story. It's nothing special.
Thank you. Any other question, please? Very quick, please.
Tell me, please, do you apply your multivalued theory to cold magnetized plasma, where a dusty plasma, where a non-linear structure can appear?
I did not have a chance of doing so yet. I did not have a chance of doing this yet, and I leave it to some of my students to do this, okay?
I have a quick comment.
Yeah.
Contrary to your expectation, rather than a criticism, I have nothing but praise. I think this multi-value theory is very deep, and I will discuss it with you privately, but definitely I recommend you to apply to biology. Because of reason that for a multivalence, I don't want to take time now, apparently biology demands multivalence, so it's very, very deep. So contrary to your expectation, I will criticize. No, I'm doing the opposite. I'm supporting you. Thank you, excellent talk, indeed.
I have a final comment. I think a very important message of Professor Agent talk is that, on the contrary of what lots of people think, torsion is an intrinsic, even if hidden, property of general relativity. I'm correct?
Yes, yes.
Right, yeah.
Yes, that's correct.
You're right, sure.
Yes. Okay. Very well.